Hello, welcome to video lectures. Today's topic is simple bending theory. Myself, Karanam Rao, Assistant Professor, Vijayanagara College, Hosapete. What is simple bending theory? When a beam having an arbitrary cross section is subjected to a transverse loads, the beam will bend. In addition to bending, the other effects such as twisting and buckling may occur. And to investigate a problem that includes all the combined effects of bending, twisting and buckling could become a complicated one. Thus, we are interested to investigate the bending effects alone. In order to do so, we have to put certain constraints on the geometry of the beam and the manner of loading. Now we shall understand what are the constraints. These constraints on the geometry would be in the form of assumptions. Then what are the assumptions that we put? The beam is initially straight and has a constant cross section. Beam is made of homogeneous material and the beam has longitudinal plane of symmetry. Longitudinal means lengthwise. Resultant of applied loads lies in the plane of symmetry. The geometry of the overall member is such that bending and not buckling is the primary cause of failure. The elastic limit is nowhere exceeded and E is the same in tension and compression. Plane cross sections remains plane before and after bending. Now let us understand what is this bending moment. A beam is defined as a rod of uniform cross section whose length is much greater as compared to its other dimensions, so that shearing stresses over any cross section of it are negligibly small. They are usually set in horizontal position and are designed to support heavy loads. They are used in building to support roofs and in bridges to support the load of vehicles passing over them. That means it acts like a bridge between any two surfaces. Let us consider a beam of uniform rectangular cross section, which is represented as shown in figure as you have just seen. A beam may be assumed to be consisting of number of parallel longitudinal metallic fibers placed one over other and are called filaments. It is just like a lamination of thin sheets which is placed one over another, which each layer or each thin film which acts as a filament. So it is the coordination of thin sheets called as filaments. Under the bent condition, the convex side of the beam, that is bulged portion, is extended, while those on the concave, the one which is below the bulged portion, is concave and is said to be compressed. In between these filaments, this is neither lengthened nor shortened, but remains constant in length. This filament is called neutral filament, and the axis of the beam lying on the neutral filament is called a neutral axis. Further, the deformation of any filament can be measured with reference to the neutral axis. Now let us understand what is the bending moment of the beam. Let us consider a section of the beam that is in the form of A, B, C, D is a section of the beam which represents a small longitudinal bent beam which is being bent over a small angle. PQ represents a filament at the neutral surface. P', Q' is another filament which is at a distance y from PQ. In a bent beam, PQ and P', Q' are arcs of a circle having their centers at O and of radii R and R plus Y respectively. If theta is the angle, and that angle it may be POQ or P', then we have PQ is equal to R theta. That means the length of arc, that is PQ, is equal to R into theta. It is similar to that of S is equal to R theta. S is the linear displacement, R is the radius of the arc, and theta is the angular displacement. In the same way, the length PQ the length of the arc PQ is equal to r into theta, where r is radius, theta is the angular displacement. Similarly, for the arc P dash Q dash, it is given by r plus y into theta. Up to Q, it is P. It is nothing but the length is r. And from up to P dash Q dash, the total radius is r plus y into theta. The change in length produced in the filament PQ due to bending is given by P dash Q dash minus PQ. P dash Q dash is P r plus y into theta minus PQ is r theta. Now on simplification we get this as y into theta. Then what is the external tension on the filament? That is nothing but change in length to the original length, that is given by y theta by r theta. Since the beam is not subjected to either shearing or bulk strain, the extensional or compressional strains on the filaments are due to the forces acting along the lengths of the filaments. If y is the Young's modulus of the material of the beam and the longitudinal stress on the filament, F B dash Q dash is given by y, capital Y into small y divided by r. If A is the cross-sectional area of cross-section of the filament, then what is the longitudinal force on the filament? Longitudinal force is nothing but stress into area, that is given by y, capital Y, small y, A divided by r. Then what is the moment of the longitudinal force about the neutral axis? That is nothing but force into distance. The force, as we have seen just now, capital Y, small y, A divided by r into distance is y again. That is equal to A capital Y, small y square divided by r. As the moment of the force acting on both the surfaces, that is upper and lower halves of the section, are in the same direction. That means the total moment of the force acting on the filaments due to straining is given by summation of all such values taken over one complete area, that is given by sigma a y square into y by r, or y by r into sigma a y square, where sigma a y square is geometrical moment of inertia and is equal to a into k square, where a is the total area of cross section and k is the radius of gyration of the beam. Radius of gyration of the beam, and the quantity sigma ay square represented as Ig. Ig is the geometrical moment of inertia of the bar. The total moment of forces acting on all the filaments is called bending moment, and this bending moment is given by capital Y by r into sigma ay square is nothing but capital A k square, where k is radius of gyration. It is at a point from the axis of rotation at which the complete mass of the body is assumed to be concentrated, is called radius of gyration and is the measure of distance. The bending moment of the beam is given by Ig into y by r, where Ig is equal to A into k square. That is nothing but geometrical moment of inertia of the bar, that is given by Ig. For rectangular cross section, if B is the breadth and D is the thickness of the beam, then area A is equal to BD and K square is equal to D square by 12. Then Ig is equal to AK square, that is equal to BD cube by 12. That means in place of Ig, if you substitute BD cube by 12, then we get bending moment for rectangular cross section and is given by y by r into BD cube by 12, or that is equal to y BD cube by 12r, which is called bending moment of rectangular cross section, which is given by y BD cube divided by 12r, or it can also be written as y by r into BD cube by 12. It is easy to remember. It is easy to remember as y by r into BD cube by 12. For circular cross section, if r is the radius, then area of the circle is pi r square and k square is r square by 4. However, Ig is equal to a k square. Ig is equal to a is pi r square. K square is r square by 4, that is equal to pi r to the power of 4 by 4. Substituting the value of Ig in the bending of a beam equation, then the equation becomes bending moment for a circular cross section is pi y r to the power of 4 by 4r. In other words, we can rewrite this as y by r into pi r to the power of 4 by 4. Y by r into pi r to the power of 4 by 4. This can be written as two terms. First term is y by r. Second term is pi r to the power of 4 by 4. Therefore, bending moment for a circular cross section is y by r into pi r to the power of 4 by 4. Thank you.